Why with tau? Because Lee and his colleague found the stride length was related to flight time of the athletes in the air, and the flight time was proportional to vertical impulse of the athlete. In other words, they adjusted their stride length by their vertical impulse. But how they adjusted the vertical impulse is the flight time information was incorporated with the time to contact information. So remember, the tau variable was from the relative expansion of optical expansion of an object. So as they near the target, their relative optical expansion, the rate ratio, will indicate the time remaining to contact the target, the plate. So because they can estimate the time, they can adjust the flight time, which means they can adjust the vertical impulse, and as a consequence, the stride length adjustment is made. This use of tau information in the after sixth stride, within the sixth stride of the last takeoff, is regardless of the skill level. So it does not depend on the skill level or of the expertise. And not only the long jump, but also the normal walking situation, the similar adjustment was made. So they had target and they were just walking normally, and their results indicated for the start of the last fourth stride, their variability began to decrease, which means they made adjustment from the sixth last stride and towards the target. So adjustment was made at the last moments, and it was because of the funnel-like control using the tau information. Slightly different topic, but it's also related to visual perception. And first I will explain this because it's related to stair climbing, related to locomotion also. When the subject were asked to choose the climbability of the staircase, so whether they can climb in one go or not, climbability. Let's have our stair here. So if it's the leg, climb with normal, not using the hand or just normal climb. When they had different height of the climb, the stair rise, which is represented by this diagram as R, the maximal height of the stair was actually related to L, which means if they were shown, the subject were shown different height of the stairs and asked, can you climb this, and the subject say yes or no, the climbability in 50% of chance was related to 88% of the person's leg length. So stair step height and person's leg length. In other words, R over L was about 0.88. This is the graph. They had two groups. One was tall group and the other one was short group. So this asterisk one is the short group and the tall one is this triangle group, the tall height. And when they graph the percent climbable, in 50% of chance through the error. The short group said, well, about 28 centimeter, they say it's climbable or not, and about 33 centimeters, the tall group says in 50% of chance it's climbable. When this one is represented by the ratio between the leg length and the stair height, two groups, the results from the two groups were identical, which means the ratio R over L, the 50% of chance, they say about 0.88, the ratio, and there were no difference between short and tall group. So it was body scale information that they used to judge the climbability of the stairs. Similarly, Warren and Wong, and this first study was to look at the passability of the doorway. So what it means is there's two columns and the subject were asked to pass that doorway without any shoulder rotation. So as they reduce the width of the doorway, there was at some point the subject had to turn the shoulders to pass that doorway. And similarly with the stair height experiment, at some point either whether the shoulder width was bigger or smaller, the body scale between the shoulder widths and widths of the doorway the ratio was constant across the subject, regardless of their body size. So widths of the doorway and the shoulder widths. Was 1.3. So which one was bigger? The doorway opening over shoulder was 1.3, which means they actually had the safety margin, so it's bigger. They identify a bit bigger than their shoulder widths as the possible doorway without rotating the shoulder. So those two examples show that our visual perception directly affects our action, and it is by the body scale information that we use